Okay, welcome everybody. So, last time we ended with a discussion on using separation of variables to solve um, a BVP-IVP for the one-dimensional wave equation with Dirichlet boundary conditions. So, this was the wave equation in question. So this is, if you recall the physical interpretation of what's going on here, this was vibrating string with two fixed ends, right? So this was vibrating string with two fixed ends. And of course, maybe we should think vibrating finite string, right? I have to tell you it's finite, so the ends aren't at infinity or something like that. Okay, so this is a finite string modeled by thinking about placing the ends at 0 and at L. So the length of the string is L. And these ends are fixed, right? So the vibration is happening between here, right? So that's what these homogeneous Dirichlet boundary conditions mean. Okay, so I have two fixed ends for my string, and I want to find solution. Now, way back when we were first talking about this stuff, um, our method of dealing with this was pretty complicated because of all the things we had to consider, right? We had to count how many reflections occurred in each of the regions in question, right? You remember that picture that we drew of the domain of influence and dependence. Maybe I'll just show that on screen again. Let's see, here we go. So for this problem, the domain of influence and dependence looked like this. The numbers here indicate counting the numbers of reflection that happen in each region, right? So these are the number. This is the number of reflections um, that have happened for points in each region, and this is, for instance, what the domain of influence would look like for some initial disturbance here at x naught. This is my domain of influence, and you see how nasty and complicated it is in the finite case, right? But we use separation of variables to overcome all of that complication and find that actually even from that picture, what that picture told me was that in order to do this, I'm going to basically have to find solutions in a bunch of pieces and then sum the pieces, right? So that solution is actually kind of hinting that this is what we ended up finding is basically the form this thing has to take. But we found using separation of variables, right? So our normal approach, seek separated solution. This gives rise to two eigenvalue problems, right, for x and t. We know exactly what this one is. This is the Dirichlet problem, right, for this eigenvalue ODE, and it has the canned solutions that we've already discussed, right? Sine of n pi x over L with eigenvalues n squared pi squared over L squared. The associated Fourier series for the initial data that's going to come up once we impose the initial conditions is, of course, this thing. All right. So that gives us eigenfunctions for x and eigenvalues lambda. We plug those eigenvalues lambda into our second eigenvalue problem, and now we know how to solve this. We don't have initial conditions here, so we we get a general solution, right, in terms of coefficients c sub n and d sub n. And ultimately, this led to a solution to that problem of the form where this is an infinite sum of the product of those eigenfunctions, right? So it looks like this. Now imposing the initial conditions, right, where I have an initial displacement phi, initial velocity c, gives me that I can determine these coefficients c sub n, d sub n in the following way. So c sub n is 2 over L times the integral from 0 to L of phi of x sine of n pi x over L, which is just the Fourier sine coefficients of phi. And d sub n, right? So to impose this initial condition C, I need to take a time derivative of this thing. It only hits this part. Because of taking this time derivative, cosine becomes a minus sine becomes a cosine. Plugging in 0, the sine terms go away, and so I'm only left with the cosine terms. And d sub n is going to be multiplied by n pi c over L times sine of n pi x over L, which leads me to this expression. To find such a d sub n, as I told you, one way you can do this is write a sub n as this quantity. Then a sub n are the Fourier sine coefficients of c. So you know what that is. It looks like this, except with a c instead of a phi here. But then to solve for d sub n, you just divide that by n pi c over L. So d sub n is 2 over n pi c times the integral from 0 to L of c of x sine of n pi x over L. Okay, so these d sub n's are not exactly the Fourier sine coefficients of c. They're the Fourier sine coefficients of c with this thing multiplied by them, right? Okay. But we found c sub n, d sub n, and so what is the solution to this original PDE boundary value problem? Well, it is u of xt, which looks like this, where the c sub n and d sub n's are determined by these formulas. All right, so that's what we did at the end. Now, let's see how this applies to a specific example. So consider the same BVP IVP, where I've actually specified phi and c. Okay, so let's have a look. So now consider, so this is like a sub-example, but I'll write it as another example. So now consider the following BVP IVP for the wave equation. Which is u sub tt is c squared u sub xx. And my Dirichlet boundary conditions are the same. They're homogeneous. So this is u of 0. T is the same as u of L. T, which is 0. And suppose that my initial displacement is sine of, we'll say, 27 pi x over L. And let's suppose my initial velocity is 0. Okay. So then what does a solution to this look like? Well, I know that my solution is of this form. Okay, with c sub n and d sub n, coefficients determined by these integrals involving my initial data, phi and c. And so, in this particular problem, note, right, phi of x is, my initial displacement is sine of 27 pi x over L. And c of x is identically 0. Right? And so, u of xt is the sum from n equals 1 to infinity of, here I'm just copying this formula over, this one. So I'm just copying this formula over. So this is sum from n equals 1 to infinity of c sub n cosine of n pi ct over L plus d sub n sine of n pi ct over L, okay, times sine of n pi x over L. Okay. Where now I'm just copying my formulas for the coefficients, C sub n and D sub n. So remember yesterday I was saying, like, what if I gave you one of these problems that we've technically already done. We've done the general case of it, right? We've done it for general initial conditions. Say that I give you one of these problems. Everything's the same, so I pick Dirichlet or Neumann conditions, whatever, and everything's the same, but I give you a specific function, right, for your initial data, x squared, right, e to the minus x, whatever initial data I give you, and then I ask you to solve it. Well, you might say, what does it mean to solve it? I can just plug the phi into the formula I'm given and say, yep, that's the solution. But no, what I mean by that is I want you to explicitly compute the coefficients. I want you to compute all of those integrals so that you give me a closed form expression for those coefficients if possible. Right? That's what I want. And so that's exactly what we're going to do here, right? We were given a specific phi and c. We were given specific phi and c, and I want to actually compute these integrals. So here's what my solution looks like, where c sub n is equal to, I'm just going to write this is 2 over L times the integral from 0 to L of phi of x sine of n pi x over L. Phi of x here is sine of 27 pi x over L. So this is sine of 27 pi x over L times sine of n pi x over L dx. But by orthogonality, right? By orthogonality, what do I get here? Right? What do I get here? Sine of 27 pi x over L times sine of n pi x over L, and I'm integrating that from 0 to L. Remember the orthogonality relations, right? You just proved in your last homework. This tells me that this quantity is equal to, well, it is 0 if n is anything other than 27, right? So this is 0 if n is not equal to 27. And if n is equal to 27, then this would be sine of 27 pi x over L squared, right, in this integrand. And the integral of that, the integral from 0 to L of sine of 27 pi x over L squared dx, is L over 2. So this would be 2 over L times L over 2. So this would just be 1 if n is equal to 27. Okay. And d sub n is even easier to compute. Right? So d sub n is what? D sub n is 2 over n pi c times the integral from 0 to L of c sine of n pi x over L, right? Remind ourselves from the formula. So this is, but c is identically 0 here, so this is just 0 times sine of n pi x over L. It doesn't matter what n is here. This is 0 for all n. And so this solution that I got is substantially simpler than this because all of the c sub n's are 0 except 1 when n is equal to 27. And all of the d sub n's are 0. So let's rewrite that, right? Thus, u sub x, or u of xt is what? So all of the c sub n's are 0 except when n is equal to 27. All the d sub n's are 0. And so this, I no longer need an infinite sum. There's a single term here that pops out. And that single term is what? This is cosine of 27 pi ct over L times sine of 27 pi x over L. This is my solution. Okay. And for some types of problems, this is exactly what you end up with, right? So your recipe for the solution involves an infinite series, but it may turn out that most of those coefficients are zero, right? And so you will get, something like this. You might immediately recognize this or remember this because we only had a look at this a couple weeks ago, right? But way back when we first talked about these finite string problems, I gave this as an example of a solution to a BVP just like this for the wave equation. Okay, and now we've shown via separation of variables that this is in fact the solution. It is the solution we're looking for that solves this problem. But I want you to notice a couple of things, and I'll track some of these on the next page. But the thing is that I want you to notice is sine of 27 pi x over L, that you've seen before in this problem, that's just phi. Right? That's just phi. And so what this solution basically is a multiplication of the initial displacement, right, by some multiple, right, that you can think of this as like the amplitude part of this. And so what it is that you have your initial displacement actually showing up here in the solution in this direct way, and the solution itself ends up being like just a multiple of it in a sense, right? And so this is giving a specific nice example for what's going on here, and I want to try to interpret this, okay, physically. Okay, so note a couple of things. Note. So one, if we input an eigenfunction, of course, we had a specific eigenfunction here, but returning to this, what if instead of sine of 27 pi x over L, I had picked sine of 37 pi x over L? Well, the exact same thing would have happened, right? If my velocity was still zero, the exact same thing would happen, and instead of these coefficients picking out the 27th term, it would have picked out the 37th term, right? If I had chosen an initial displacement that was like a sum, right, of a couple of these eigenfunctions, then again, the same sort of thing would have happened. It would have picked out, say, the 27th and the 37th, right? Or whatever two values here that you had used. It would pick out those terms. Okay, so choosing like an initial displacement that was an eigenfunction had a direct like consequence that led to this simple form of the solution, right? And this is something we could more generally think about for other types of problems. What happens when I choose an eigenfunction for this initial displacement? Because, of course, there's absolutely no reason why I have to do this. The phi of x could have been x squared e to the minus x, times cosine of x, right? It could have been any of those things, right? It doesn't have to be an eigenfunction, clearly. It could have been whatever. But when it is an eigenfunction, you get something special happening, right? With a lot of these coefficients being zero, right? Okay. And so if we input an eigenfunction as the initial displacement, for this problem. Okay. Then the solution at any time t is simply a constant. Now you might object here, and you might say, wait, it's not a constant, right? Cosine of 27 pi ct over L is not a constant. Well, for any given fixed t, it's a constant, right? So for a fixed t, this is some constant times this initial displacement, right? And so at any time t, this is a constant times the initial displacement. Which means I've just scaled the amplitude, right? So i.e., it is some amplification of the initial displacement. Okay. Okay. What does that mean? It means, right? So this means that the basic shape is preserved here, right? So if you go back to thinking about this initial disturbance as being like a signal that's propagated in some way, then it means that the shape of that signal, that initial signal, is preserved, right? So in particular, this means that the basic shape is preserved. Okay. Now, some terminology here. We call such eigenfunctions, right? If we've used an eigenfunction as our initial data, okay, in this way, an initial displacement, we call such eigenfunctions normal modes of the string. So we call such eigenfunctions normal modes of the string. Okay. Now, note also that if we fix a position x on the string, the displacement oscillates. So now what we're doing, let's go back to what our solution looks like. So for this first bit, we were fixing a position on, or sorry, we were fixing a time, t, and noticing that, oh, like for a fixed time t, this solution is just an amplification, some constant, times the initial shape, right, this initial displacement. But now, if we think in reverse, if we fix a position x, right, for a fixed position x, looking at this solution, well, it's going to oscillate, right, governed by this cosine term. But we can actually just directly compute the frequency here, right, of this oscillation, because it's just a cosine term, right? So what is its frequency? Well, its frequency is 27 pi c over L, right? So note also that if we fix a position x on the string, the displacement oscillates with frequency equal to 27 pi c over L, which of course is C times the square root of this particular eigenvalue, lambda sub 27. Okay. These associated frequencies are called the natural frequencies or natural harmonics of the vibrating string. So these frequencies are called the natural frequencies or harmonics of the string. Okay. Of course, you could say how many of these special solutions exist? Well, we have one for each eigenfunction, right? Like those solutions, you choose an eigenfunction. One of our countably infinite eigenfunctions is your initial displacement and velocity, initial velocity 0. You're going to get exactly those solutions that look like this for generic n, right? So that every solution is a linear combination of those special ones, right? So that's the key thing. So maybe kind of in conclusion here, say we choose initial so initial displacement phi of x, which is one of the eigenfunctions, so sine of n pi x over L for n a natural number. Okay, and c of x identically equal to 0. So we've chosen initial displacement and velocity as follows. There we go. Okay. Then we have solutions u of xt, which is sine of n pi x over L times cosine of n pi ct over L. And that's, we have that as a solution for every n in the natural numbers, i.e. every solution is a linear combination of these special ones. And so these special solutions like build any given solution to that problem. Okay, which is pretty amazing, right? So think about what that means physically in terms of fixed string, right? That basically your solution, right, your general displacement at position x time t, right? So that displacement can be given entirely as linear combination of these terms associated to the natural frequencies, the normal modes, right, the harmonics. So that's pretty nice. So in a sense, those harmonics are like the building blocks of your solution. Okay. All right. So that's a cool physical application we're finally able to return to, right? It's been a long time since we considered the finite string wave equation, but now we've returned to it and we're able to actually say some stuff about it thanks to the power of separation of variables. So that is good. We're very happy, hopefully. Okay. Another example. Let's do finite string wave equation with homogeneous Neumann boundary conditions. Right? So wave equation. with homogeneous Neumann BCs. All right, and so recall what those look like. So I have wave equation, u sub tt is equal to c squared u sub xx. Okay, and x is between 0 and L. All right, I have my finite string, and t is greater than 0. I have Neumann conditions now at the boundary, so u sub x of 0t is the same as u sub x lt, which is 0. That's what the homogeneous means. Right, so t is greater than 0. And then I, again, have completely general initial displacement phi and initial velocity c. And x, again, is between 0 and L. Okay. So I want to do exactly what I did before, right? So separation of variables. I seek a solution that is separated. What does this lead to? This leads to eigenvalue problems of the form. For x, the eigenvalue problem associated is x double prime plus lambda x is equal to 0. And the boundary conditions here, these Neumann boundary conditions, descend to Neumann boundary conditions for my eigenvalue problem. So x prime of 0 is equal to x prime of L is equal to 0. So that is my eigenvalue problem for x. My eigenvalue problem for t is similar to the previous example of the wave equation. So this is t double prime plus lambda c squared t is equal to 0. Okay. So these are my two eigenvalue problems I get. Okay. Now, what do I find here? Right? So, first of all, now, like I always do, how do I solve this eigenvalue problem? I have my canned solutions going back to my list of eigenvalue problems. Here we go. For Neumann boundary conditions for an eigenvalue problem, which is exactly what we have, the eigenfunctions and eigenvalues are cosine n pi x over L with eigenvalues n squared pi squared over L squared. Now, 0 is an eigenvalue, so that's something I have to remember here in this case. Of course, here's the corresponding Fourier series and so on, okay, which should factor into this somewhere. So, the eigenvalues and eigenfunctions for this problem, so eigenvalues are lambda sub n, which is n pi L over L all squared, and n is 0, 1, 2, and so on. So we do have 0 as an eigenvalue here. And eigenfunctions are given by x sub n of x, which is cosine of n pi x over L. Okay. Now I have to think for a second about how to correct this situation. For all I have to do, I know exactly how this is going to work. In fact, you might have already kind of like finished this in your head of how this goes, right? These lambda sub n's go here. I can immediately write t is now, a linear combination of cosines and sines, right, of m pi ct over L, with coefficients that come from, if you had to guess, you're probably going to say these are the Fourier cosine coefficients, and you would indeed be right that that's how that's going to work. But then the question is, I have to take care of this lambda not, right, lambda equals 0 eigenvalue case separately to make sure that when I write this, the form the solution takes, I get everything right. So what do I do here? So note, if lambda is equal to 0, okay, if lambda is equal to 0, then in this eigenvalue problem, I have x double prime is equal to 0 with Neumann boundary conditions. which means that the term on the x is 0. The constant term is going to be the only thing left, right? So if lambda is equal to 0, x double prime is equal to 0, which implies that x of x is like, I'll write it as ax plus b. Okay, but if x prime of x I know is just a, but x prime of 0 is x prime of L, which is 0, which implies that a is equal to 0. And so the only solutions I have to this eigenvalue problem for the lambda equals 0 case is x equals constant, right? Is only solution if lambda is equal to 0. Of course, if lambda is equal to 0, then plugging in 0 here, I also have t double prime is equal to 0. And so what I end up getting is that t of t is, I'm going to write these constants as like c naught and d naught, right? So this is like c naught plus d naught t is my general solution to this. Remember, for the t equation in this problem, I don't have any more conditions, so I get the general solution here with coefficients showing up. Okay. So that takes care of the lambda equals 0 case. When lambda is 1 or bigger, then this proceeds as it always did. And so what's my full solution? Now, my full solution is going to be the normal series term, summed from 1 to infinity, and then the lambda equals 0 term is going to be what's outside the sum, right? And that's going to be this thing. And so, thus, my solution, right? So that's my solution, right? My full solution is u of xt is the lambda equals 0 term, which x is just a constant that's reflected here, and t is this thing. So you might say, wait, isn't for the lambda equals 0 term, don't I have a x sub 0 times t sub 0? Yes, you do, but this is just a constant, so we've absorbed that in c naught and d naught. And so this is c naught plus, I need to make the constant term match up in a single formula, of course. I want to introduce a factor of 1/2 here, like I normally do when I'm dealing with the cosine Fourier series. So this is 1/2 c naught plus 1/2 d naught t plus the sum from n equals 1 to infinity of c sub n cosine of n pi ct over L plus d sub n sine of n pi x over L, all times cosine of n pi x over L. Why is that not a sine? Because remember, our eigenfunctions here are cosines for this case instead of sines, right? Okay. So this is my full solution, where imposing the initial conditions yields what? So let's impose the initial condition that we know phi of x has to be u of x 0. And so u of x 0 here, plugging that in, so there's a 0. Oh, I put an x here. That's wrong. This is a t. There, now we have a hope that this is actually correct. Okay, and so plugging in a 0 here, this is 1. These terms are 0. And so I'm going to have 1, so this is 0. I'm going to have 1/2 c naught plus the sum from n equals 1 to infinity of c sub n times cosine of n pi x over L, which of course is going to do what here? So this is going to tell me that the IE I should choose c sub n to be the Fourier cosine coefficients of phi. All right, so i.e. c sub n should be 2 over L times the integral from 0 to L of phi of x cosine of m pi x over L dx, and that's for n equals 0, 1, 2, and so on. Okay. Let's have a gander at what I would do to impose the other initial condition. I need to take the derivative of this with respect to t and evaluate it at t equals 0. So c of x is the derivative of this with respect to t evaluated at t equals 0. So what do I get here? So I take the derivative with respect to t. This term's 0. This term becomes 1/2 d naught. Plus here, my cosines become minus sines. My sines become cosines. Doesn't hit this term at all because it only depends on t here. And so this becomes cosines, but I have I have an m pi. Why did I not have a c here? I have an m pi c over L outside here. So this becomes, so this is u sub t of x 0. This is 1/2 d naught, right? Because I took the derivative here, so there's no t to evaluate. Plus the sum from n equals 1 to infinity of here, like I said, this becomes a minus sign times some constant. I don't care. When I plug in 0, I get 0. Here, this becomes n pi c over L times d sub n times cosine of n pi x over L. Okay. And so the idea here is that, again, I'm in this situation, right, where I have, well, because of this stupid thing, right, this is kind of annoying because the n equals 0 case is kind of annoying, but this is going to be the Fourier cosine coefficients with this thing scaled in some way. So practice. What form should d sub n's take? They're not exactly going to be the Fourier cosine coefficients, right? But just like before, my idea here, right, is to try to rewrite this as like an a sub n. If I do that and define a naught to be d naught, right, then what I get are the Fourier cosine coefficients. I can find out what I can write those things out, and then see how that gives me a formula for my d sub n's. Of course, if you can't figure out how to write this in one single, closed form formula, if you have to separate out, like here's what d naught is, and then here's what d sub n is for n greater than 1, that's fine if you want to do it that way. But this is good practice for you to write out explicitly what the d sub n's are. But we see that exactly as before, like once we've done this, we're very happy to say we've solved the problem. We've found the C sub n's and D sub n's, and here's what my solution looks like. You can verify for yourself if you want to. This does indeed solve. Uh, this does indeed solve the problem that we started with, which was wave equation with homogeneous Neumann boundary conditions. Okay, so there it is. All right. So now what? Let's do more examples, right? More examples. So how can we do this with more examples? Well, let's just keep going, right? Let's do inhomogeneous Dirichlet boundary conditions. How do we treat those? How do we treat these? Let's do it for the heat equation. So let's do this for the heat equation with some different boundary conditions. These sorts of ideas, you can think about how they would apply to the wave equation if you were kind of try to do the same sort of methods. And so, what is it that should go on here, right? So first, let's write this out and see what kind of problem this causes for our process and how we can try to fix it. So inhomogeneous Dirichlet boundary conditions for the diffusion equation, we'll say. Although you can think, as I said, about how this would apply to other equations. So let's consider the problem that is u sub t equals alpha u sub xx on finite bar, we'll say x is between 0 L, t is greater than 0. We have inhomogeneous Dirichlet boundary conditions, which means that I have differing temperatures. So remember my physical interpretation of this, right? And this is for t greater than 0. So t naught and t1, they don't have to be equal. They don't have to be 0. And we have some initial condition. Okay. Now, what is the problem here, right? So the problem, I guess, kind of the first thing you notice is if we want to proceed with separation of variables, because separation of variables algebraically really depends on the structure of this thing first, then our analysis that we've done in every single example should work in exactly the same way, right? i.e., we should get some eigenvalue problem, or we should get two eigenvalue problems, and then we want to solve them. But the problem is that for these eigenvalue problems, one of our assumptions for these boundary conditions was that I had these boundary conditions equal to 0, right? So that's a little different. Now, it was a question even back then, whether this process or whether we could do this thing for symmetric boundary conditions. And, we of course defined it for three very easy boundary conditions, right? The simplest form of Dirichlet, Neumann, and we also had periodic boundary conditions. But the question is, could the boundary conditions be something else? The answer was yeah, as long as they were symmetric boundary conditions, which we defined, then this was okay. And you can check for yourself whether or not you think these are an example of symmetric boundary conditions. But nevertheless, this process has to change from what we have written here just because these boundary conditions are slightly different, right? They're not both equal to 0, right? They could be different things. So what is the idea here, right? So the idea, first, look for steady state solution, right? Which we said is if you like, it's this thing, right? we can define the steady state solution. Since we're taking the limit as t goes to infinity of this thing, this expression should not depend on t. Right? We'll call that v. Okay. So note, if this is going to be a solution to the heat equation, but it's steady state in the sense that its t derivative is 0, we've written here it doesn't depend on t. So the point is that what should this satisfy? The u sub t term now has to be 0 because this doesn't depend on 0 anymore. So I get 0 is equal to alpha v sub xx, but these partial derivatives are full derivatives of v. So if this is going to be a solution to this heat equation, this steady state solution has to satisfy v double prime is equal to 0. Right? But v double prime is equal to 0, I have initial conditions here, right, which are v of 0 is equal to t naught, and v of L is equal to t1. Now, you might say to yourself, wait, you just called those initial conditions. Those are boundary conditions. They're not initial conditions. Well, yeah, they're not initial conditions, but I have moved on to this world of now, forget about all this stuff, I have an ODE, right? I have an ODE with, and that means, you know, I'm only considering one variable here, x. These derivatives are with respect to that one variable, so these are full derivatives. And so in this context, these are initial conditions for this ODE, right? Now, I know that's a little confusing, and you don't have to think of it that way. But the point is, I have conditions for this ODE that I can impose on solutions, right? And so this is a boundary value problem where I know immediately, right, this, just from this, v of x has to be like ax plus b. But then what do these conditions tell me, right? So v of 0 has to be t naught, but v of 0 is equal to b, so that's what b has to be, right? And v of L has to be t sub 1, but then that also has to be a times L plus b, which is t naught. And so A is T1 minus T naught. So the temperature at the left end minus the temperature at the, or sorry, the temperature at the right end minus the temperature at the left end divided by L. And so our steady state solution is of the form T1 minus T naught over L times X plus T naught. Okay. All right. And so, what does this equation, what does the steady state solution tend to? What does our solution to this tend to as t goes to infinity? It tends to a linear interpolation between the two temperatures, T naught and T1. Right? Okay. Now, define W of xt to be u of xt, where u is a solution to this, minus this steady state solution. So I subtract off this steady state solution. This is a very important step. And you might say to yourself, like, why would I ever think to do this? Well, the reason you'd think to do this is there's a couple of things, right? You get some tools in your tool belt once you've dealt with a certain type of problem a bunch of times. And one of these tools is this whole time, right, something we've used over and over and over again, is the fact that for linear equations, we can abuse the principle of superposition, which is because they're linear, they respect linear combinations. So if I have a bunch of solutions, right, to a given differential problem, okay, I can take a sum of those things, or a linear combination even. So scalar multiply those things by whatever I want to, and then sum them all together, and that is still going to satisfy. Right? They are still going to satisfy the underlying relationship. Okay, but this only works for linear problems. But we're in good shape here because that's exactly what we've got going on. And so, like, why would I think to do this? Because I notice, right, that if I define W to be this thing, then firstly, what does this satisfy? Right? So firstly, let's look at the boundary conditions here. What is W of 0t? Well, that is U of 0t minus V of 0. U of 0t is t naught. So this is t naught. Minus V of 0 is also t naught. So this is 0. And W of L of t is U of L of t minus V of L. But then this is U of L of t is t1 minus V of L, which is also t1. So this is also 0. So W actually has homogeneous Dirichlet boundary conditions. Well, that's great and all, but that doesn't help us at all if it doesn't also solve the PDE in question that we're interested in. Oh, but wait. Let's ask ourselves, right? What PDE does W solve? So what PDE does W of xt solve? So recall, W of xt is U of xt minus V of x. Well, what about its initial condition, right? So what is W of x0? Well, this is U of x0 minus V of x. But U of x0 is phi. So this is phi of x minus the steady state solution V of x. Okay. Again, we have come up with a bunch of conditions that this thing solves. So it has homogeneous Dirichlet boundary conditions. It has an initial condition that's pretty simple. It's just phi minus the steady state solution. And so, so this is just some other given, right, initial data that we actually know, right? And so the question is, what PDE does this thing solve? Well, if I take W sub t here, right, then this is equal to what? This is equal to U sub t, right, x of t. Well, the partial derivative of this thing with respect to v is 0, right? So the partial derivative of w with respect to t is U sub t minus 0 here because the partial derivative of v with respect to t is 0. Okay. And so w sub t is equal to U sub t. What about alpha w sub xx here? Well, this is going to be alpha times u sub xx of xt minus v double prime, right, of x. But v double prime of x is 0. So this is equal to alpha u sub xx of xt. And since U solves our original diffusion equation, so does W. And so W of xt solves the IVP BVP, which is W sub t equals alpha W sub xx, W of 0 t equals W of LT, which is 0, and W of x0 is phi of x minus v of x, where v of x is that steady state solution. All right? So this W is called the transient solution. And so this is called the transient solution, which is, what's nice about this transient solution is that it has homogeneous boundary conditions, right? We're very, very happy with that. You think of the terminology here, steady state versus transient, right? Here, what is W? It's the part of the solution U where I've subtracted off the steady state solution, right? So calling it the transient solution here definitely makes sense, right? That's good terminology. Okay. And so what do I do? So thus, I simply solve, we'll call this star for W of xt, then add to it, then I add my steady state solution v of x to it to obtain u of xt, which if W is u minus v, then u is W plus v. Right? Okay. Note that the limit as t goes to infinity of if the limit as t goes to infinity of u of xt is going to be v of x, right, as we wrote, if that's going to be the case, then this limit needs to be 0, right? So this limit needs to be 0, so that implies that the limit as t goes to infinity of u sub x, maybe I actually said this backwards, but that's fine, is this thing. Thus, calling this the steady state solution, right? It is the eventual, it reflects the eventual or long-term behavior of the system in question. And so this transient solution really is measuring like how far you are away from the eventual steady state solution, right? It's your displacement from the steady state solution, if you like. Okay. All right. And so you might say, wait, you didn't solve anything. Well, we've already done this, right? We did this in the last lecture. So we know exactly what this is, right? This is an infinite linear combination of solutions where the coefficients are the Fourier sine coefficients for now this function, right? And then so we get that infinite sum, and then to that we add this to get our solution to this problem. Okay. All right. What about mixed homogeneous boundary conditions? So let's consider the problem. It looks like this. U sub t is alpha u sub xx, where x is between 0 and L, t is positive. And let's say we have mixed but homogeneous boundary conditions. So I have a condition on u right, at the left end of 0, and I have a condition on the partial derivative of u with respect to x at the right end, and that's also 0. Okay, that's for t positive. And then I have the usual initial condition here. Okay. All right. So let's do separation of variables. Our usual thing here. So u of xt is sought as separated solution, which gives me what? So this is going to give me, what are my boundary, or what are my associated eigenvalue problems going to be? Well, as usual, right, my eigenvalue problems, are going to be x double prime plus lambda x is equal to 0, and t prime plus lambda alpha, or alpha lambda t, is equal to 0, where I have no conditions here, and now I have these mixed boundary conditions that are going to descend to what kind of boundary conditions here? Well, they're going to descend to mixed boundary conditions in my eigenvalue problem, right? This wasn't on my list, right? This wasn't on that original list I made, right? Let's just recall what was on the list. All right, so here's what the list consisted of for us so far. Okay, so we had homogeneous Dirichlet boundary conditions for an eigenvalue problem, and we had our canned eigenfunctions and eigenvalues. We had homogeneous Neumann boundary conditions for our eigenvalue problem, and we had our canned eigenfunctions and eigenvalues. Very similar, but now we have cosine series showing up instead. And then lastly, for our periodic boundary conditions for our eigenvalue problem, we had two eigenfunctions associated to every non-zero eigenvalue, and our eigenvalues again were the same, but we got, like I said, two eigenfunctions associated to each non-zero one. And then the Fourier series showing up here was now the full Fourier series, right? Okay. Well, as it turns out, we can do this, but we have to know what our eigenfunctions and eigenvalues are in this case. So how can I know that? Well, I can do this analysis that led to the solutions to begin with. So it's just some ODE stuff that I did, right? So by that same ODE stuff, we can do this for these mixed boundary conditions. And so in order to write these out, let's just go ahead and add an entry to our list, right? So we'll say addendum mixed boundary conditions. So our eigenvalue problem is the actual ODE structure is the same, but now we have homogeneous mixed boundary conditions. Like this. So this is the type of problem we have, just to remind ourselves. Yep, that was the problem we had. So this is what we want our canned eigenfunctions and eigenvalues for. And so this turns out that I get eigenfunctions and eigenvalues. That look like as follows. So x sub n of x is sine of n plus 1/2 pi x over L, and lambda sub n is n plus 1/2 squared pi squared L over L squared, and n is 0, 1, 2, 3, and so on. Okay. And you can check directly by integration if you want to that when you pair this eigenfunction with itself using the inner product, right, this thing paired with itself, this is the integral from 0 to L of sine squared of n plus 1/2 pi x over L dx, that what you get is indeed L over 2. So the corresponding Fourier series is sum from n equals 0 to infinity of a sub n sine of n plus 1/2 pi x over L, where a sub n is, as usual, it's phi paired with x sub n over x sub n paired with itself. Right, these are general Fourier series coefficients. This is 2 over L times the integral from 0 to L of phi of x integrated against these eigenfunctions. So sine of n plus 1/2 pi x over L dx. Okay. So this is, so addendum to the list. I now have canned solutions, so canned eigenfunctions and eigenvalues for mixed boundary conditions, homogeneous mixed boundary condition problems. Okay, and as I said, you can obtain those in the same way we got the others. It just takes a little bit more work. I mean, well, it actually takes the exact same amount of work. It's just the thing that you're doing is just slightly more complicated. Okay. And so, let's return to our problem now. Well, I just said that wasn't on my list, but now I just put it on my list, right? So there's my eigenfunctions, there's the associated eigenvalues. Okay, and so, copying those over, right? So this is lambda sub n, so I get eigenvalues. Lambda sub n is n plus 1/2 squared pi squared over L squared. Okay, and corresponding eigenfunctions, x sub n of x, which are sine of n plus 1/2 pi x over L. Okay. Plugging these eigenvalues into this eigenvalue problem for t yields solutions t sub n of t equals some constant c sub n e to the minus lambda sub n of times alpha of t. Okay, the usual, right? Thus, doing our usual thing, right, where I have found eigenfunctions t sub n, eigenfunctions x sub n, considering u of xt as sum of, so infinite sum, say from n equals 0 to infinity of the x sub n's, t sub n's, what do I get here? Right, well, this is thus my solution. Is u of xt is the sum from n equals 0 to infinity of c sub n times sine of n plus 1/2 pi x over L times e to the minus lambda in alpha t. I'm going to write that entirely in terms of, so I'm going to write this as e to the minus n plus 1/2 squared pi squared alpha t over L squared. Okay. And so imposing the initial condition, right, as usual. So here's my solution. In order to find what the C sub n should be, I have to impose my initial condition. So imposing the initial condition, phi of x is u of x0, which is, thankfully, I plug in 0 here, and so this just becomes 1. So this is the sum from n equals 0 to infinity of c sub n sine of n plus 1/2 pi x over L. Well, it turns out that this is another example of one of these orthogonal families here. And so it turns out that if you compute, for instance, as we did before, x sub n paired with x sub n, remember this is the same as the length of x sub n squared. This is L over 2. So we have the same sort of orthogonality thing going on here. And so it turns out the coefficients are given by, it's not the Fourier sine series, but it's like similar to the Fourier sine series, right? So it turns out that by orthogonality, exactly how we always do this, right? We pair phi with x sub n, right? And then find that, oh, actually, right? So like what this means is that phi paired with x sub n is equal to c sub n times x sub n paired with itself. And so c sub n is equal to phi x sub n over x sub n paired with itself, which, as we wrote before, since this is L over 2, this is going to be 2 over L times the integral from 0 to L of phi of x times the eigenfunctions x sub n, which are these signs. So that's sine of n plus 1/2 pi x over L dx. So this works in exactly the same way, right? So that was mixed homogeneous. It turns out we can also do this for mixed inhomogeneous, right? We can talk about inhomogeneous Neumann boundary conditions, which we are going to do too, at least talk about what the process is here. We're even going to talk about the Robin boundary condition for the diffusion equation. If you remember the physical interpretation of that, maybe I'll remind you tomorrow. And we will see how all these things work together with Duhamel's principle. And you might have noticed that we have not talked about one of the big three in this thing. So we've done separation of variables algorithm for the heat equation, for the wave equation, at least in 1D. We'll talk about how to handle higher dimensional stuff a little bit, but the overall process is essentially the same. Then there's one noticeably absent mention here in the big three, which is Laplace's equation. So the question is, how does separation of variables work for Laplace's equation? Because Laplace's equation is kind of weird that it doesn't have a time right? It doesn't have like the time slot. So in a weird way, since we talk about the dimension of our problems in terms of the spatial dimension. So the simplest Laplace's equation, right, that's not trivial to us is the 2D case. So already we're dealing with a two-dimensional thing. We'll see how all of that works in the next lecture. So that'll be a big focal point of next lecture, is finally seeing how this works for Laplace's equation. Okay, so anyway, that is that, and I will see you all on Monday.